So in this video we're going to complete the derivation of the spectrum or dispersion relation of quantum phonons. And well, this part as well as the previous part is a bit technical, so I will actually skip some of the calculations and we'll just show you sort of the method, illustrate the method, which is called, by the way, Bogoliubov transformation, that is used to solve such a problem. And as a side remark, let me mention here that, well, this material that I'm going to be covering is actually a pretty advanced graduate material. So if you got to this point, you should be proud of yourself. This is a very complicated, very advanced material of quantum many-body physics you're actually studying. So in this slide, I would like to review the calculations we have done so far, sort of tell you where we have been and also where we're going with this. And as we know, we started with this classical oscillator chain, which is characterized by the coordinates and momenta of all the atoms in this one-dimensional crystal. And the first step in putting together a quantum problem was to quantize this, which means basically to replace the variables x and p with the operators. And so we just put hats on top of x, p, and h. So the following step involved expressing these momenta and coordinates with the corresponding creation and annihilation operators, which led to this complicated looking Hamiltonian. And here this A_n and A_n dagger correspond to creating an oscillation in a particular site with a particular atom labeled by n. So the next step that we took in the previous segment was essentially to Fourier transform these creation and annihilation operators and to express them in the Q space, in the wave vector space, if you want. And the corresponding Hamiltonian is shown here. So it has, as you can see, two types of terms, A dagger and A, and this A, Q, A minus Q. And so now we have to work with these operators, these new creation and annihilation operators, and this Hamiltonian. So, and now I'm coming to where are we going with this. So, if we did not have, let's imagine for a second that we do not have this term. Let's say we have just this term. So if this were the case, it would have meant that we already solved the problem. The reason for this being that this linear combination, the integral after all is a linear combination of these A dagger A's, independent A dagger A's, they sort of correspond to a collection of independent harmonic oscillators, the spectrum of which we know perfectly well. So for each Q, we have basically a simple harmonic oscillator, such as in the previous lecture, and we know its spectrum. And now we just collect these oscillators and write them as an integral, but all in all, we know the result. So this is essentially already a solution. And therefore, this A of Q, or more precisely actually due to the Hermitian conjugate part here, twice A of Q, would have been the spectrum of our problem, the spectrum of this quantum phonons. But of course, we do have this term. We do have this term, and we don't know what to do with it, right? So the spectrum of this Hamiltonian is not at all obvious. So a way to solve the problem now is to actually construct a new set of creation and annihilation operators. So here I have an operator B, which is an annihilation operator of a new type, and there is also a B dagger of Q. And so let's assume that we can construct this B and B dagger as a linear combination of A and A dagger in such a way that the new Hamiltonian won't have the bad terms. By bad terms, I mean the terms that we don't know how to deal with. And instead, we'll have only this sort of standard combination of B dagger and B, for which the spectrum is obvious. And so this essentially would mean to solve the problem. The ability to write the Hamiltonian in this form, in the form of a linear combination of some creation and annihilation operators of this sort, so would mean to solve the problem, and this twice this A tilde would give us the dispersion relation of these B's, which actually are the quantum phonons. So as we will see, so this B dagger hat and B hat, they correspond to creation and annihilation operators of quantum phonons, essentially the normal modes, the quantized normal modes in this oscillator chain. But together as well, as you can see, is rather non-trivial. First we have to do this quantization, and then, well, which was simple, but then we have to do at least 3 linear transformations to get to this point. And this last linear transformation is what is actually known as the Bogoliubov transformation. So here's a picture of a young Nikolai Bogoliubov, who was a very influential and talented mathematical physicist, a Russian mathematical physicist. And he was an author of many very important works, and also he came up with a number of very important and practical mathematical methods that are used up to these days. And one of these methods is this Bogoliubov transformation that we're going to be studying. And let me mention that this Bogoliubov transformation is still used very actively in research papers. So I myself have used it in a number of my published works. And this is basically, in some sense, an everyday tool of theorists working in quantum physics and in condensed matter physics, as well as perhaps high energy physics. So this is an important method. But well, in the example that we're going to be considering today, so the method is rather straightforward, and I already advertised sort of a motivation for using this method. So let's look again at this Hamiltonian that we have for the original the creation and annihilation operators a sub q, dagger and a sub q. So, and again, as I said, so our sort of a strategy would be to correct in some sense the definition of the creation and annihilation operator, so that we can get rid of this unwanted term. And if you look at this Hamiltonian, you will see that this Hamiltonian involves essentially, so if we didn't have this term again, so we would have had just a linear combination of independent q operators. But this term, the appearance of this term couples the q mode with minus q mode. So whatever transformation we come up with, it should probably involve a linear combination of at least aq and a minus q. So let me just present a form, sort of knowing the result, of course, is easy, but it will save us some time. So let me just present a form of this generic Bogoliubov transform that accomplishes what I want, namely that introduces new operators. In this case, these are these operators b sub q and b dagger sub q, which are linear combination of a and a dagger, or vice versa. A and a dagger are linear combinations of b and b dagger is here. And so here I will assume, and this assumption will be verified sort of a posteriori, and let me assume that these coefficients can be chosen to be real numbers, well, functions better to say, and that they're even functions of q. So u of q is equal to u of minus q. So in this case, actually, this second definition here is redundant because the second definition of the creation operator can be obtained from the definition of the annihilation operator simply by applying the Hermitian conjugation. But in any case, so let us assume that we can construct such operators. So the first thing we need to do, and this is, I'm basically describing the strategy of constructing Bogoliubov transforms, is to make sure that this b and b hat are indeed creation and annihilation operators. So I can call them such, but actually this should have a precise mathematical meaning. And the precise meaning would be that these guys, so let's say if I have b of some q and b of p, let's say dagger, so these guys should be, the commutator of this guy should be 0 if q is not equal to p, and it should be a delta function otherwise, so infinite otherwise in some sense. So this is what I'm looking for. So my a and a dagger, so the reason I call them creation and annihilation operators was that they satisfy this relation. Now I want the new operators, which are actually a linear combination of those, to satisfy the same commutation relation. So, and this would involve a calculation which would result in a constraint on these coefficients u and v. So if I calculate this commutation relation that I already know, so this is the commutator of a sub q and a dagger sub p. So I simply plug in these definitions to here and this guy to here, with replacing q with p, and I just calculate the commutators term by term. So what I can write, I can just write, so I will have 1, 2, 3, 4 different terms. So the first term, let's say, will be the commutator of these two guys, so such as here, and using this constraint I will require that the commutator of these two guys will be 2 pi delta function of q minus p. Now these two commutators, which result in this term, should give me 0, because these both are actually annihilation operators. So likewise these two guys resulting in this term should give me 0 as well, because these are commutators of the creation operators. And so finally I have a term which couples b dagger of minus q and b of minus p. And since the commutator of b dagger is equal to, well, this delta function, the commutator of b dagger and b is basically minus the commutator of b and b dagger, and so it should give me this function. And let me remind you that the delta function involved here is actually an even function, so it doesn't really matter that I have here minus signs, etc. So, and if I put everything together, so these guys basically go away, right? So these guys go away, and I have these two terms which essentially all involve the same delta functions. And also, since there's a delta function here, q is actually pinned to p. So the delta function is 0 if q is not equal to p. And so there are only terms, therefore here I can simply write it as, let's say, u sub q squared, and this guy will be v sub q squared. Now with the minus sign. So if I put everything together from this expression, so this is what I get, okay? And now I have to require that the right-hand side reproduces what is supposed to be in the left-hand side. That is this 2 pi delta function of q minus p. So which means that this coefficient here, so this u squared minus v squared, must be identically equal to 1. And this introduces a constraint, an important constraint on this Bogoliubov transformation. So, so basically what we're doing here, again, so let me sort of go back to where we're going with this. So we want to put together these new operators, and so we want to find explicitly the expressions for this u sub q and v sub q that, first of all, would ensure that this b and b dagger are indeed annihilation and creation operators of something. And second, another constraint on these guys would be that the resulting Hamiltonian, now expressed in terms of b and b dagger, would be simple enough so that we know its solution. And this is basically the essence of Bogoliubov transformation. So in this case, this Bogoliubov transformation is relatively simple, and actually in most cases you will see in the literature, even the research literature, it is relatively simple, but in general it may be more complicated. So it doesn't necessarily have to include just two terms, it may include more terms. But in all these cases, so the strategy would be the same. So basically, to ensure that the operators you introduce are indeed creation annihilation operators, and second, then they simplify or Hamiltonian. So now we can sort of keep this constraint in mind, or we can resolve it once and for all by just using new parameterization, if you want, of this u and v. So, and this can be achieved by using the following mathematical identity. So if we introduce u of q being a hyperbolic cosine, so let me remind you that the hyperbolic cosine of some x is equal to e to the power x plus e to the power minus x divided by 2, and the hyperbolic sine of x is equal to e to the power x minus e to the power minus x divided by 2. So this is a real, in some sense, real version of the sine and cosine, in which case I would have had the measuring constant I here. But in any case, so these guys so satisfy the following identity, which is sort of an analog of the identity that most of you know, that sine squared plus cosine squared is equal to 1. So here for the hyperbolic functions, I have the hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. And this is exactly the identity that I want for my u and v. So so if I use this parameterization, which resolves this identity once and for all, so which basically reduces the problem with two parameters to a problem with just single parameter, in this case this is this lambda. So my sort of expression for the creation and annihilation operators a and a dagger now becomes this, okay? So I have A of q is equal to cosine hyperbolic of lambda bq plus sine hyperbolic of lambda b of minus q dagger and the corresponding A dagger. All right, so now what needs to be done is that we have to just do a brute force analysis. We have just go ahead and plug in these expressions into the Hamiltonian. And I will leave it for you, for those of you who are interested, for those of you, for instance, who are interested in becoming theorists, or who are theorists, or who are mathematicians, or who are just curious about the technical part. So you can go ahead and do the simple, relatively straight, it's not, I'm going to call it simple, it's a straightforward exercise of just plugging in, let's say, instead of this guy, here we're going to put this linear combination, instead of this guy we're going to put this linear combination, etc. And so if you do so, well, you will see some unpleasant algebra, but this is an exercise I'm sure you can do it. So in here I'm showing the result of the calculation. If you do everything correctly, this is what you should get. And the result here is a Hamiltonian, which now is expressed in terms of these new operators, B of q and B dagger of q. And as you can see, it has the form which is pretty much the same as we had before, just with some new coefficients, which I call now A tilde and B tilde. And here is the expressions for these coefficients involving hyperbolic cosines of 2 lambda and hyperbolic sines of 2 lambda. And these are the original coefficients in the Hamiltonian for A's. And so you may ask me, what, why did we bother to, introduce new operators if we got exactly the same thing? So, well, the answer to this, and actually this brings me to the second step in this Bogoliubov transformation, is that, well, lambda here is a free parameter, so better to say a free function. We can choose this function any way we see fit. In particular, we can choose it such that this unwanted term, the bad term that we don't want to see, is identically equal to 0. So we essentially can set by hand this B tilde of q equal to 0, which leads to an equation for lambda. So this equation, as you can see from here, if we just move this guy to the right hand side and divide by cosine, so sine hyperbolic over cosine hyperbolic is tangent hyperbolic. So the tangent hyperbolic of 2 lambda of q is equal to minus b of q versus over a of q. And so this essentially gives us a specific result for this lambda of q, which ensures that our Hamiltonian, in terms of this new creation annihilation operators, looks simple. So now let me clean it up a little bit and sort of summarize things again. So this is the result that we got. And also let me remind you that this A of q and B of q, the original coefficients, we already know. So we derived them in the previous part of this lecture. And so let me remind you their explicit form. So here's their explicit form. So this is explicitly B of q and this is explicitly A of q. And well, I wrote it sort of explicitly this way, but as you can see, a lot of things here cancel out, including this H omega, and there are a lot of other simplifications involved. And if you play around with this, well, with these coefficients, if you do a little bit of algebra, you will see that, well, first of all, lambda of q actually determines, as you can see from here. So this guy is 0 as we wanted it to be. But now this guy is determined by lambda, and we do know lambda. So we simply can plug it, in here. And if once everything is said and done, you actually have an explicit expression for this A tilde of q, which becomes, in the end of the day, surprisingly simple. So again, this calculation is not obvious from here. It requires a little bit of work, and due to the format of the lectures and lack of time, I'm not presenting it. But those of you who are interested, of course, can go ahead and check that this is indeed the result. So this is by construction, but A of q has this form. So if we plot it, so this A of q has this form, which is actually a very familiar form. So this is A of q, which we have seen before in the classical problem in the context of acoustic phonons. And this is exactly what they are. But now they're quantum phonons. So sort of to summarize the result and also to emphasize a very important point, so this is what we actually got. We have found explicitly a series of linear transformations of the original Hamiltonian, of the original operators involved in the Hamiltonian, such that the Hamiltonian can be was casted in this form, which is a so-called diagonal form of the Hamiltonian. Sometimes if you happen to read research papers, the researchers call about diagonalization of a Hamiltonian. This is what it actually means. So to diagonalize the Hamiltonian in a problem which involves many quantum particles essentially means the ability to write it as a linear combination of independent oscillators of some other particles, the sort of behavior of which we know very well. And so this is exactly what we've accomplished here. And so here we have also this Hermitian conjugate. So if we calculate it, it will be simply the same term. So we can write it integral over q, well, twice a tilde of q, b dagger q, bq. So, and well, I should also mention one thing that I sort of swept under the rug, and this thing is that I haven't paid attention to constants that appear in the Hamiltonian. So there could be a constant here. If I had done it, so the correct result that I would have found is, well, this is correct, but there also is a constant term here which corresponds to 0-point motion, and this term happens to be exactly 1/2. So if you remember the solution to the simple harmonic oscillator, we have essentially h omega and plus 1/2, and so similarly it appears here. So in this 2a tilde of q is exactly the energy modes of the oscillator. So we can call it, so this guy is equal to h omega of q, and this would be the spectrum of the quantum phonons. And this is presented here. So the spectrum of the quantum phonons here is twice omega. Omega here is the frequency of a single oscillator. In some sense, in the original classical picture, it would have been the frequency, the natural frequency of the spring connecting the atoms in some sense. And so the remarkable thing that I want to emphasize in the very end, and this will be the end of today's lecture, is that it turns out that this spectrum of quantum phonons is actually identical to the spectrum of classical phonons. There's absolutely no difference whatsoever. So if you go back to the problem that we solved earlier today in today's lecture, so namely the classical problem, so it was slightly more complicated in the sense that it involved two types of atoms. But if we had just one type of atom, so this is the result which we would have got. So an important conclusion of this sort of discovery that quantum and classical phonons turn out to be exactly the same is the following. So we can say that we could have quantized our problem at any stage. So in the solution I presented, we did so at the very beginning. So essentially converted the original coordinates and momenta of the atoms into quantum operators, x hat sub n and p hat sub n. And then we went ahead with this quantum calculation, the Bogoliubov transform. But instead of doing that, sort of, there is a second version of the solution. One could have solved the problem, the classical problem first, and which means finding the trajectories of particles and the corresponding waves. And so one could have quantized these normal modes. So basically, so the normal modes can be converted then into these essentially operators h omega q, some b dagger q bq plus 1/2. So we could have done that. And the results, basically, we have proven that the results are exactly the same. And this is very important. It shows us something about the quantum to classical correspondence. And this quantum to classical correspondence sort of persists also in more complicated problems, let's say problems in 3 dimensions with more degrees of freedom with different types of atoms. And this is true as long as we have non-interacting theory, which in the language of these creation and annihilation operators essentially means a theory which is bilinear in these b's and b daggers. So as long as we have these bilinear forms, we're fine with this quantum to classical correspondence. But once we have more complicated nonlinear terms, so this situation becomes much more complicated. So the last thing I'm going to mention is that the appearance of such terms, which we're not going to discuss at all, but if we had these quartic terms, b dagger, bb, for instance, so they would have meant that the phonons interact with one another. So in some sense, it would have corresponded to scattering of waves of each other, waves running through the crystal. And this is a very complicated challenge to understand the behavior of such an interacting system, and there are still ongoing theoretical challenges in describing it, so it's definitely beyond the scope of this course. But this theory is well understood, and I hope some of you got an idea about phonons and collective modes in classical and quantum physics.